All right, guys. So this is your pre-recorded video lesson for the week of April the 20th through April the 24th. So you're going to want to go into Google Classroom and click on Science. Go over to Classwork. You're going to scroll down and you're going to click on NTI Assignment Must Do, April 20th to April 24th, Science NTI Assignment. You're going to see the Google slide presentation that I am about to go over, and then your assignment, which is just a Google form this week. So you'll click on the Google form, you will fill out your name, your group, and there are 10 questions regarding the video lesson. You may retake this as many times as you want to get a 10 out of 10. All right. So let's go through this investigation. Last week, you learned what a wave is. A wave is a disturbance caused by a vibration. This week, we're going to learn what the properties of a wave are.
You are looking at a new world record for the wave. Attempt, can they do it? 168,000. They are here from the Guinness Book of World Records to certify the record if they can make it all the way around. Yes, folks, just another sellout crowd here at the world's fastest half mile in Bristol, Tennessee. Looks like it's getting off turn two pretty good. Get a little momentum down the backstretch here. Gotta get it to turn three. We're gonna have a record if they can make it all the way around. They would break the record by some 50,000 fans. And they have done it, folks. Here they come, a new world record for the wave. 168,000 fans have jammed their way in to watch what has historically been a stock car slugfest.
Okay, so doing the wave is an example of a wave-like phenomenon. Waves are repeating and regular patterns. They're predictable when their properties are constant. So when we think of wave-like phenomenon, we need to think of things that share those characteristics. Can you think of other examples of waves or wave-like phenomenon that you see in your everyday lives? Some examples might include a simple wave of the hand, if you are saying hello or goodbye. Another example would be a swing, a grandfather clock, a pendulum going back and forth. Those are all examples. Now, the basic properties of waves are amplitude, wavelength, frequency, and speed. To understand the properties of waves, it helps to represent a wave on a diagram. Transverse waves, like those on a rope, are easy to draw as shown below. If you have a scratched piece of paper, it might be a good idea to get one out and draw that diagram, and as we go through the properties, label them. So you have something to look at as you are taking the Google or doing the Google form assessment or assignment. Okay, last week we talked about two kinds of waves, a transverse wave and a longitudinal wave. We are just going to focus on transverse waves this week to identify the properties of a wave, and then we'll come back and talk about the properties of a longitudinal wave the week after. So a transverse wave is just a wave that moves the medium. So it moves the particles of a solid, a liquid, or a gas at a right angle to the direction in which the wave is traveling. So if the wave is traveling at a horizontal direction as seen in the video, okay, the medium transfers perpendicular. So if I pause this, you can see that here, the original resting position was straight across here. And if I draw a line straight down, a vertical line, it's going to transverse this horizontal line. That's a perpendicular line crossing a horizontal line, and that makes a right angle. So we call a transverse wave for that reason, okay? Transverse just means across. And so the medium would transverse or go across this center line right here, or the original rest position. So as a transverse wave moves in one direction, the particles of the medium move across the direction of the wave. All right, here we have two more examples. On the right-hand side, let's start here first. We've got a y-axis and an x-axis here, and we're going to pretend that this x-axis, this black line, is a rope tied to a door. And that rope is just being pulled with a lot of tension. It's being pulled very tight. And I'm going to move that rope up and down like the picture on the left. Well, I'm going to freeze that rope. Now, in the real world, you can't freeze it, okay? But we can pretend. And this blue line now represents that rope frozen, okay? This horizontal line right here, this is the rope's rest position. It's also called the center line. As the wave passes, the rope will go above and below this rest position. The crest are the highest points of the wave, and the troughs are the lowest points on the wave. Some waves can be very high, while some waves are barely noticeable. Amplitude is the maximum distance the particles of the medium carrying the wave move away from the rest position or the center line. So the rope would be my medium. It's a solid. And the amplitude is how far the particles in the rope moved away from its rest position. The amplitude is a measure of how much a particle in the medium moves when disturbed by the wave. And the amplitude is going to be measured from the rest position, another word for this is the center line, to the top of a crest, or from the center line or rest position to a trough. Another example you can think of is a water wave. So you can actually go in your kitchen right now and do this quick demonstration. If you get a bowl of water and let the water come to a calm, you can imagine that surface level is the resting position. And if you disturb the water is going to start to make waves. Well, the water goes above the surface and below the surface. So that's just another example of amplitude in a transverse wave. We're also going to look at another model. So what I want you to do when I play the model is to see if you can identify which part of the chain model represents these two terms. So remember, a medium is the material through which a wave travels, and amplitude is the height of a wave. Let me get my parameters set here. There we go. So which part of this model represents our medium and which part represents our amplitude? If you said the red and green beads represent our medium, you're correct. The red and green beads are a solid, and that's the material the wave is traveling through. And then if you said how tall the beads went represents our amplitude, you were correct. So let's go back and talk about this. So our red and green beads here represent the matter. This is the medium or the matter that the wave is traveling through. The amplitude is how high the beads are from its resting position, from either the resting position or center line to the crest, or the center line to the trough. So if I restart this, there's my resting position. It's not moving. Now I'm going to start to move it up and down. And you can see that amplitude is just how high the wave is from its original position. Now, if I wanted to make the wave much higher, I would need to give the wave more energy. And if I wanted the wave to be a lot lower, I would need to give it less energy. Now, this is a limitation to this model. So if you look down here, I can change my amplitude. In the real world, you can't change the amplitude like this. To change the amplitude, you would physically have to give it more energy or less energy. Well, I'm going to take our amplitude up to the highest here and show you how our height is going to change based off the energy. Check that out. So our amplitude is much higher. And then I can take it all the way down. And you can see how that's barely noticeable. Like it's barely going above the center line. Okay. Wavelength. So a wave will travel a certain distance before it starts repeating again. The distance between two corresponding parts of a wave is called its wavelength. And you can find the wavelength of a transverse wave by measuring the distance from crest to crest or trough to trough. So let's practice. We're going to go back to that model, and I want you to tell me which part of the chain model represents the term below. So wavelength is the distance between two high points or crest in a wave or two low points. So looking at your model, what part of this would represent the wavelength? If you said from crest to crest or from trough to trough, you would be correct. So it's how far apart the high points or low points are. Okay? All right, let's talk about frequency and speed. So oftentimes students will get, and sometimes adults too, will get frequency and speed mixed up. So wave frequency is the number of complete waves that pass a given point in a certain amount of time. If you make a wave on a rope so that one wave passes by every second, the frequency is one wave per second. Since waves are vibrations of a medium, frequency can also be described as the number of vibrations per second. To increase the frequency of the waves on a rope, you can make more vibrations by moving your hand up and down more often, say 2 or 3 times per second. If I wanted to decrease the frequency, you would move your hand less often, once every 2 or 3 seconds. Frequency is measured in units called hertz. Now, speed is very different. I want you to imagine you're watching a distant thunderstorm on a hot summer day. First, you see a flash of lightning, and then a few seconds later, you hear a roll of thunder. Even though the lightning and thunder occurred in the same instant, they reach you seconds apart. Well, this happens because sound and light travel at different speeds. Light travels much faster than sound, and different waves travel at different speeds depending upon the medium as well. So we'll talk more about light and sound waves in the next couple of weeks, but light is part of the electromagnetic spectrum, and all of the different kinds of electromagnetic waves travel at different speeds. And then depending upon if it's a solid, liquid, or gas, that changes the speed of a wave as well. The speed of a wave is how far the wave travels in one unit of time or distance divided by time. So now let's look at our model again, and we are going to talk about which part of our, chain model, not slinky model, represents these two terms. So frequency is the number of waves per second, and then speed is the wave traveling the same distance, but in a different amount of time. So let's go back to that model. All right. So for frequency, we're going to do a couple of examples here. And I'm going to give you a set time, let's say 10 seconds. And I'll try my best. This is going to be very hard for me. So this isn't going to be very accurate because I can't start the wrench up and down or the timer up and down. But I'm going to press play and we're going to count how many waves go by a certain point in that amount of time. So let's focus on one green bead, okay? Okay, I counted 7 waves and I wasn't able to stop it exactly at 10. So we'll go ahead and just round back down to 10 to just for the sake of doing the math. Okay, so if it's 7 waves in 10 seconds, I want to know how many waves it was per second. So I'm going to take 7 waves divided by 10 seconds, and we have 0.7th of a wave every second. So this is a pretty high frequency. Okay, let's try it again. If you remember, if we go back, how can I decrease or increase the frequency? If my frequency right now is 0.7 waves per second and I want the frequency to be higher, then I would need to move the wrench more often. Well, I was already struggling. So I'm actually going to decrease the frequency. So let's try this again. We're going to do 10 seconds. All right, counted 4 waves. So this time I'm going to do 4 divided by 10. 4 waves in 10 seconds is 0.4th. So it's 0.4 of a wave. So I was able to decrease the frequency. I can try it one more time to see if I can get more waves in that 10 seconds. So let's restart it. I'm going to press play and see if you can keep up. Okay, I counted 16. Is that what you got? I hope so. So now I'm going to take 16 and divide it by 10. And now we have 1.6 waves per second. So I was able to increase the frequency here. Okay. All right. Now let's talk about speed. Speed is different. So speed is a wave traveling the same distance, but in a different amount of time. Okay. So we're going to count how long it takes this wave to go from the wrench to the window. Okay. Now, it's going to be hard for me to start and stop this. So we're going to kind of just have to watch the start time and the finish time. All right. So, ready, set, and it didn't even take a second for this to go from the wrench to the window. Okay. Now, we're going to do the same thing again, but I'm going to show you how I can change the speed. And I'm going to use that. I'm going to do that using this tension bar down here. So this tension bar changes the tension of this material. Right now, this is pulled really, really tight. We're going to pretend that this tension is allowing me to change the medium. So we're going to say this is a solid. And if I take the tension down really low, this is now traveling through maybe a gas. Okay. Now, in the real world, that's not what tension is. Tension is how taut or how tight the object is, also depending on the material of the object. Okay. So a wave, let's say this was a sound wave. And initially it traveled through that solid or that gas in like 1 second. Well, now it's going to travel through a different medium. Okay. And we're going to notice it travels a little differently. So we're going to time how far it goes from the wrench to the window. Ready? Same wave. You can see that's taking a lot longer to travel through. Okay. And we'll talk more about how a medium affects the speed of a wave down the road in a couple of weeks. Let's go back. So, how often the wrench moved up and down represents our frequency, the number of waves per second. How quickly a wave moved from the wrench to the window is the speed. Waves traveling same distances but in different amounts of time. So those are the 4 properties of a wave. Last thing I want to talk about before we wrap up is energy. We learned last week that waves carry energy, okay? They transfer energy. Now, in future lessons, we're going to learn that waves can also carry data or information, but for now, we're just going to think of waves in terms of their ability to transfer energy. In the beaded chain model, did the whole chain ever change its position? Why or why not? No. Once the wave moved through the chain returned to its original position. The beads of the chain moved up and down with the wave, but they did not move to a new location. This is because only the energy that transferred from the hand to the chain was moved to the end of the chain. The particles of the chain vibrated faster because of the increased energy, and that made them bump into their neighboring particles, causing the disturbance or wave that carried the energy to the end of the chain. The matter stayed right where it was. And that ends our presentation. Don't forget to fill out the Google form sheet and turn in your work by Friday, and let me know if you have any questions.